In this video, we're gonna see how we can do a colocalization study with ImageJ. So for this study, we're gonna focus on this image so let me open the channels tool, and I'm gonna just switch off everything but the first channel. So in red, we have the endoplasmic reticulum. In green, we have the Golgi. In blue, we have the nuclei. And in gray, we have helix spermatial lectin. And as you can see, is very much localized in the Golgi. So we're going to first look at the colocalization between those two, so between the Golgi and the lectin, to see if we actually have colocalization. So I'm going to start by splitting a channel, so image color split channels. And now I'm going to use a tool that comes with Fiji. If you go to Analyze Colocalization, you have something called Coloc2. So here you need to define the channels you want to study the colocalization between. So here, as I said, we want to look at the Golgi, C2, and the lectin, C4. And we're first going to start with a 2D intensity histogram. So the histograms look like this. So you actually have here the intensity in channel 1, here the intensity in channel 2. So for each pixel you look at, the intensity you have in one and the other channel, and then you compute a histogram. So basically, if you look at this part correspond to pixels that have a high intensity in channel 1, but very low intensity in channel 2. Okay? So now if we look at this histogram, we can see that we have this region and this region. And I want to say that in this region, it's even two different regions. You have one that is here, corresponding to pixels that have low intensity in both channels. So if we go back to the channel, this is the lectin channel, and this is the Golgi channel. So pixels for which the intensity is low in both channels correspond to pixels that are in the background in both channels. Then we have quite some pixels that have a larger intensity in channel 1, but still a low intensity in channel 2. And it makes sense because if you look at this region, for example, it's not very high intensity, but it's definitely not black in this channel. And here it's definitely in the background. And finally, you have this region that corresponds to pixels that have a high intensity in both channels. So basically, if you see something like this, it means that you probably have colocalization. Now we can also look at, in this report, we can look at the person correlation R value, and you can see that it's high. The maximum value for a person R value is 1, so if you have 1, it means very high colocalization. If you have 0, it means nothing. If you have -1, it means repulsion, anti-colocalization. So here it's all high, so with or without threshold. Threshold defined as the cost, as defined by the cost method. So here it definitely means that you have some colocalization. Now, as you can see, we have this region where we have lots of pixels in the background. So if you look at a different image and you just want to look at the colocalization in a given region, especially, let's say you look at some tissue and you have background is going to somehow pollute your analysis because you're going to have pixels that have low intensity in both channels, which in some way is, it means colocalization. It doesn't, it really depends how you compute everything, but still, it's gonna probably bias your analysis, or it could. So you can definitely define ROI, and let's define a ROI here where we have lectin, okay, and we can compute again the 2D histogram, and given this image is now so we need to define C2, C4, the ROI. So the ROI is in C4, so we can click here, or it's also channel 2 is defined as C4, so this works, both works. And if we compute the 2D intensity histogram, now we only have pixels that have high intensity in both channels, and it makes sense because we restrain this analysis in a region where we have lectin, which coincides with the Golgi. Now let's do a final analysis. We're gonna try other methods. So if we go to analyze colocalization and Coloc2, we're gonna try this time Fermentous correlation and the cost significance test. So the cost significance test is a permutation test on the Pearson correlation. So you compute the Pearson correlation between your images, and then you permute. You block permute your images, and you compute again the Pearson correlation. And if your Pearson correlation is really higher when you don't permute, you're gonna have a low p-value. All right. So it takes some time because you need to permute, but here we just defined a permutation of 50, which is pretty low, and we can look at the results. So if we look at the p-value, so it's not actually the p-value. You need to do 1 minus the cost p-value to get your p-value, which would be 0 in that case, highly correlated. And if we look at the Mendel's coefficient, we have quite high here, lower here, so it's in Mendel's M1. So it means that it corresponds at, when you look at this channel, you segment it. So you're gonna have the Golgi, and depending how you segment, you're gonna have also probably more region, larger. And then you look at the intensity in this region, normalized by the average intensity over the whole image. And so so that's actually I'm wrong. It's the other way around. If we segment this, it's small region. We also have region where the intensity is outside this region. And that's why the M1 is lower. You see, M1, so auto threshold of CH2. CH2 is C4. So you threshold this, you look at the intensity in this region, and you normalize by the average intensity in the entire image. And as this is just a subpart of the Golgi, at least we have all the pixels with high intensity. It might be noise in that case, but still, that's what we have, and that's why the Mendel's coefficient M1 is lower than M2. Now, we can also do colocalization between regions that actually, sorry, that's not what I wanted to do, but actually do not coincide, do not share the same location. If we look at the nuclei and the endoplasmic reticulum, we see that the endoplasmic reticulum is not in the nucleus, so it's a 2D image, and the fluorescence is not perfect, so we have sometimes some intensity in the nucleus, some endoplasmic reticulum intensity in the nucleus, but mainly you see we see these holes corresponding to the nuclei. So now let's do a 2D histogram between those two and look at the Pearson correlation between those two. So I go back to Analyze, Colocalization, Coloc2, and I'm going to choose C1 and C3 this time. I'm just going to look at the 2D intensity histogram and the Pearson correlation. So it's very interesting. When you look at the histogram here, you have basically you have two regions and maybe a fuzzy region in between, but you have this region corresponding to pixels that have low to high intensity in channel 2 and low intensity in channel 1, and this region that have low to high intensity in channel 1 and low intensity in in channel 2. Yeah. And so that's pretty typical of repulsion, because you see that the pixels, they have either high intensity in one channel and low in the other, or vice versa. If we look at the Pearson correlation, pretty interesting too. If you don't use the threshold estimated with the cost method, you have a Pearson correlation that is almost zero, meaning no correlation. Now, if you just look at the pixels that have an intensity above the threshold estimated with a cost method, now you have a Pearson correlation that has a negative coefficient, minus 0.53, and pretty low, which means an entire colocalization. So you see here, if you consider the entire image, the Pearson correlation is close to 0 because you have many pixels in the background in both channels, and so that somehow pollutes the computation of your Pearson correlation. Now, if you just look at the pixels that have an intensity that is high enough in both channels, now you actually have a negative Pearson correlation R value, which means that you have anti-colocalization, which is actually what we observe here. So let's also compute, so I'm going to go back, analyze colocalization, Coloc2, and let's look at the Mendel's correlation. Okay. Oh, sorry, I didn't change. So here I did it between C1 and C2, you see, and I want to do it between C1 and C3. Don't go too fast. When you have several channels, you need to be careful. So I'm just going to do it again, colocalization, Coloc2, and now I'm going to select, so C1, C3, Mendel's correlation, okay. So yeah, now it makes more sense. We see this anti-correlation in the 2D intensity histogram. Now if we look at the Mendel's coefficient, they are actually, so this one is not high, but this one is pretty high. So maybe, you know, and it's interesting because it uses the same threshold estimated with the cost method, but the threshold estimated with the cost method was designed for Pearson correlation and not for Mendel's coefficient. And you see here, if you just look at the Mendel's coefficient, you could think that, oh, maybe I have colocalization, while, you know, just looking at the histogram, you know that it's not the case. So something you can do is that you can actually, in this report, you can see the threshold that were estimated. So 23 for channel 1 and 54 for channel 2. So I'm going to just use image J to look at the mask. So if I go adjust and threshold, so I said 23. So if I go to 23, oh, I'm too low, 23. You see that it's a very low threshold, and we have quite some pixels that actually correspond to the nuclei area. And probably this threshold, if it's fine to compute Pearson correlation, it's not really suited to compute the Mendel's coefficients. We can look at the nuclei, but it seems that it's going to be better. For the nuclei, it's 54. So let me define here directly 54. Maybe it's too low, sorry. Maybe it's too low, but it's definitely better. So we're going to use another plugin, because with Coloc2 you cannot control the thresholds. However, you can do it with a plugin that is called Jacob. So I'm going to just download it. So if I go there and I type Jacob is for just another colocalization plugin, and if you go to Jacob image J, you can download it here directly. All right. So yes, I want to download it because I know what I'm doing. All right, so I'm gonna close this. I'm gonna open the download, and I'm gonna copy this in my plugin folder. All right, I'm gonna restart Fiji. As you know now, that's what we need to do. All right, And I'm gonna, so open again the image, split the channels, color split, and I'm gonna start Jacob plugin. Alright, so you see it works in a very similar way actually. You define the channels you want to look at. So I said C1 and C3. Alright, they're here. And I want to just look at M1 and M2 coefficients. I don't want to use the cost automatic threshold. And you see you have other tabs and where you can actually define parameters, and depending on the method you use, they are in red, they are labeled in red to tell you that parameters in this tab are going to be used. So for example, if I use cost randomization, you see that you have these parameters that are related to cost. I don't want to do it, but M1 and M2 coefficients, now the threshold have to be defined. And now you see here, you can actually pretty easily define threshold. So let's define like this for the nuclei. And here, I don't want it to be too low. So that looks better. I'm not sure it's going to be good, but that looks better. So now I can analyze it. And now you see, so you have a definition as defined in the original paper, which is everything that is below 0, which doesn't make much sense. So it's going to be high all the time. By using the threshold I just defined, I have an M1 that is lower than 0.1 and an M2 that is lower at 0.1, which is likely to correspond to no colocalization. Doesn't mean that there's anti-colocalization. You cannot really tell you have anti-colocalization with Mendel's coefficient, but here it seems that there's no colocalization.